Section: Introduction. In this section, we discuss how large language models, LLMs, have transformed natural language processing, NLP, by enabling multitask processing, such as machine translation and code generation, with minimal data for adaptation. We anticipate that future research will further explore multimodal multitask processing, integrating both text and visual data. However, the current methods for generating images and videos are quite different from text generation, requiring complex training and representations. To simplify image and video generation, we utilize the same autoregressive transformer architecture found in popular LLMs, applying standard codecs like JPEG for images and AVC-H.264 for videos. A significant challenge in training these models is discretization, as continuous data like images and videos must be converted into discrete tokens. Existing generative vision models often use vector quantization, VQ, to encode visual data into learned latent codes, which then interact with language models. However, VQ methods can be complicated, requiring careful tuning of hyperparameters and a two-stage learning process that complicates model adaptation. We aim to address these challenges by employing conventional file encodings as non-neural preprocessors for discretization, avoiding the complexities associated with VQ methods and the high computational costs seen in approaches like ImageGPT. Our method allows us to train a standard transformer for image and video generation effectively. We pre-train two models, JPEG-LM and AVC-LM, which can generate images at a resolution of 256 by 256 and videos at 256 by 144 with 15 frames, achieving average context lengths of 5,000 and 15,000 tokens, respectively. Our evaluations show that JPEG-LM outperforms strong VQ-based models in image generation quality, achieving a 31% reduction in FID scores and producing highly realistic images. Additionally, AVC-LM generates videos with believable movements. We analyze the strengths of JPEG-LM compared to VQ models and find that our codec representations excel at capturing fine details in images, such as human faces and small text. Overall, our work demonstrates how traditional LLM architectures can be adapted for visual generation without the complications seen in previous methods. Our approach simplifies training and enhances effectiveness, contributing to the unification of various modalities and facilitating the application of LLM techniques across different domains. Section Summary. In this section, we discuss our approach to simplifying image and video generation using autoregressive transformer architectures similar to those in large language models, LLMs, leveraging standard codecs like JPEG and AVC-H.264 for effective discretization. Our method avoids the complexities of vector quantization and enables the generation of high-quality images and videos, demonstrating significant improvements over existing models while facilitating the integration of multimodal processing in future research. Section: Pixel Values, ImageGPT. In this section, we discuss ImageGPT, an image generation model that uses a standard language model architecture similar to GPT-2. It represents images as a sequence of pixel values, ranging from 0 to 255, scanned from the top left to the bottom right. To simplify the pixel data, ImageGPT groups colors into 512 clusters, allowing each pixel's 3 color values to be represented by a single value from 0 to 511. The model predicts pixel sequences one at a time, which is computationally intensive, limiting it to generating images of size 32 by 32 pixels. Higher resolution images, like 256 by 256 pixels, would require an impractical number of tokens. Next, we explore vector quantization, VQ, which involves two main steps: training a tokenizer and training a language model. Using VQ-VAE as our tokenizer example, we first encode an image into spatial features. Each feature is then quantized by finding the closest match in a learned codebook. The indices of these matches form a sequence of latent codes. A decoder is trained to reconstruct the original image from these quantized codes. VQVAE learns an encoder, a decoder, and a codebook, optimizing for three types of losses: reconstruction, codebook, and commitment losses. Effective training of a VQ tokenizer requires a large dataset, appropriate hyperparameters, and a careful balance of losses, adding complexity to the process. We then train a language model using the VQ latent codes, which poses challenges for updating the tokenizer after training, as it would necessitate retraining the language model. We find that even with extensive training, the VQ tokenizer struggles with less common image elements and is difficult to optimize completely. To simplify and enhance adaptability, we propose using standard codecs to discretize continuous image and video data. Although these data types are inherently 2- or 3-dimensional, they are efficiently stored as 1-dimensional files through compression. We investigate whether traditional language model architectures can learn to model and generate these standard file encodings, which can be easily opened as images or videos. This approach could significantly reduce the sequence length issues faced by image GPT and offers a simpler, end-to-end training process compared to VQ methods. We focus on widely used codecs for images and videos, specifically JPEG and AVC H.264. Section Summary. In this section, we discuss Image GPT, an image generation model that uses a conventional LLM architecture to generate images as sequences of clustered pixel values, and we introduce vector quantization models like VQVAE, which discretize images into latent codes for reconstruction. We propose using standard codecs like JPEG and AVC to efficiently model and generate images and videos, simplifying the process and addressing the limitations of previous methods. Section: Canonical codecs, JPEG and AVC H.264. In this section, we discuss canonical codecs like JPEG and AVC H.264. These non-neural codecs compress signals that are less noticeable to the human eye more aggressively. JPEG encoding involves three main steps. First, we apply a discrete cosine transform, DCT, to convert image patches into a mix of low and high frequency patterns. Next, we use quantization to eliminate some high frequency patterns that our eyes struggle to see. Finally, we employ entropy encoding, such as Huffman coding, to reduce the number of bits needed to represent the images. For AVC H.264, we work with patches of video frames called macro blocks. Each patch can be encoded using pixel blocks from the same frame, intra-frame prediction, or from other frames, interframe prediction with motion estimation. We subtract the predicted content from the current patch to create a residual, which then undergoes a process similar to JPEG, involving DCT, quantization, and bitstream encoding. The resulting encoded content is essential for container files like MP4. Both codecs have been widely used for decades, significantly compressing data compared to raw pixel modeling, about 40 times for JPEG and 110 times for AVC. Our goal is to utilize these codecs as tools to efficiently convert images and videos into sequences of discrete bytes, allowing us to fit a language model to learn the grammars and semantics of these codecs. We introduce JPEG-LM and AVC-LM. JPEG and AVC transform images and videos into bytes, with most bytes representing the content after entropy encoding. However, there are also metadata and separators that remain constant across images or videos, consuming multiple bytes. To tackle this, we extend the default byte vocabulary slightly using byte pair encoding, BPE, which merges frequently appearing byte combinations into new tokens. Since JPEG and AVC produce variable length sequences, we also add special tokens to mark the beginning and end of sequences. These entries form our JPEG-AVC tokens. For an image, we propose JPEG-LM to model the probability of a JPEG token given previous tokens. For a video, we propose AVC-LM to model the probability of an AVC token given prior tokens. We use standard autoregressive transformer architectures without any vision-specific changes to maintain the model's generality. In our experimental setup for JPEG-LM, we pre-train a 7 billion parameter Llama 2 model from scratch using 23,256 by 256 images, encoding each with a quality factor of 25. We derive 320 BPE tokens from 10,000 images, with each image averaging 5,000 tokens. For efficiency, we concatenate all sequences and chunk them into lengths of 12,000, resulting in 9.5 million sequences and 114 billion JPEG tokens for each training epoch. We train the model for about 2 epochs with a maximum learning rate of 0.0003. For AVC-LM, we demonstrate that canonical video codecs can also be used for video generation. We pre-train a 7 billion parameter Llama 2 model from scratch using 2,256 by 144 videos, keeping only the first 5 seconds at 3 frames per second, 15 frames total. We process the video with the AVC H.264 codec using a constant quantization parameter of 37. From 10,000 videos, we derive 1,024 BPE tokens, with each video averaging 15,000 tokens. We concatenate data and chunk it into context lengths of 32,000, resulting in 1.3 million sequences and 42 billion AVC tokens. Lastly, we utilize a pre-trained VQ tokenizer that was trained on 200 million images to process each image in our JPEG-LM training set. This tokenizer has a vocabulary size of 4,096 and a sequence length of 1,024. We then train a 7 billion parameter Llama 2 transformer with the same configuration as JPEG-LM, using this VQ model as a primary comparison throughout our work. Section Summary. In this section, we describe the use of canonical codecs like JPEG and AVC H.264 for efficiently converting images and videos into byte sequences, which we then model with large language models, LLMs, named JPEG-LM and AVC-LM. We outline our experimental setup, including the training of these models on large datasets, the creation of byte pair encoded vocabularies, and the use of autoregressive transformers without vision-specific modifications. Section: Image GPT plus Super Resolution. In this section, we discuss Image GPT combined with super resolution techniques. Image GPT is built on the GPT-2XL architecture and has been pre-trained on over 14 million images sized 32 by 32 pixels from ImageNet. To evaluate our results fairly, we also utilize a super resolution model based on the outputs from Image GPT. We include 2 types of diffusion models in our baseline comparisons: Stable Diffusion, which is optimized for inpainting, and VQ Diffusion. These models can take incomplete images and fill in the missing parts, a method we apply in our evaluations. Although these diffusion models are smaller, with around 1 billion parameters, they require significantly more training data, ranging from 200 million to 5 billion images. Our main focus remains on comparing autoregressive image generation models within the framework of large language models. For our results, we follow a standard evaluation method used in language modeling. We collect validation data, use parts of this data as prompts for our pre-trained models, and then sample completions from these models. We assess the quality of these completions against the original validation data using metrics like the MAV score. Since we concentrate on models that only handle visual data with LLM architectures, we use partial images and later partial videos as prompts for our models and evaluate their outputs. The autoregressive image generation models rely on a specific ratio of prompts for their generation process. In our qualitative analysis, we present generation samples from JPEG-LM alongside baseline models using independently sourced data. We find that JPEG-LM can produce impressively realistic facial expressions, landscapes, common objects, and text in images, often outperforming the VQ transformer. In our quantitative results, we evaluate JPEG-LM, VQ transformer, and other baselines using different levels of partial images from ImageNet 1K. We conduct zero-shot generation evaluations without class conditioning, using 5,000 randomly sampled images from the validation set. Our experiments, repeated 3 times with different seeds, show that JPEG-LM consistently outperforms the VQ transformer across all prompting ratios and often surpasses diffusion models with inpainting capabilities. We also validate our findings with fully unconditional generation, comparing JPEG-LM and VQ transformer on the same training data. Here, JPEG-LM again achieves a better performance score. These results highlight JPEG-LM's effectiveness as an image generation model using a pure LLM architecture. To further understand JPEG-LM's strengths, we analyze how data is processed and compressed before training in both JPEG-LM and VQ models. Both models perform compression followed by autoregressive modeling. The VQ model, unlike JPEG, uses a large dataset to train its quantizer. We observe that while both compression methods effectively handle general scenes, VQ struggles with small, significant details like human faces or text, leading to unpredictable degradation. In contrast, JPEG's degradation is more predictable, which is particularly beneficial for images containing important long-tail elements. Section Summary. In this section, we describe our approach using Image GPT, which employs a pre-trained GPT-2 model to generate images from partial inputs, and we compare its performance against diffusion models and VQ transformers. Our findings indicate that JPEG-LM consistently outperforms these baselines in generating high-quality images, particularly excelling in capturing fine details like facial expressions and text, while also demonstrating a more predictable degradation in image quality for long-tail elements. Section: Quantitative Analyses on Long-Tail Elements. In this section, we analyze long-tail elements quantitatively. We begin by examining the per-class FID in our ImageNet-1K generation experiments. For each image class, we determine the difference in FID between JPEG-LM and VQ transformer generations. We also assess how frequently each class appears online by using Google Image Search to count the total results. Our findings reveal a significant correlation between the FID differences and class frequency. Specifically, JPEG-LM shows greater advantages over the VQ model for less frequent classes, indicating that it performs better with long-tail subdistributions. Next, we explore the FFHQ images by reducing their size to half while adding a black background to maintain overall dimensions. This allows us to test how different models handle smaller visual concepts, like small human faces, which are still important for human perception. We generate images using JPEG-LM, VQ transformer, and other baseline models, and we find that JPEG-LM consistently outperforms the VQ transformer and other models. Notably, JPEG-LM performs slightly better while the VQ transformer's performance declines with the smaller images, showcasing JPEG-LM's robustness. These results suggest that JPEG-LM excels not only overall but particularly with long-tail visual elements. We also present a proof of concept for video generation. By leveraging the simplicity of canonical file encodings in LLM paradigms, we extend our work from JPEG-LM to train a video generation model called AVC-LM, which uses autoregressive transformers to model standard video codecs like AVC, H.264. We test AVC-LM by prompting it with partial videos from our training set and analyze the model's completions. Our qualitative examples show that AVC-LM effectively captures the motion of moving objects. In terms of related work, we note that current image and video generation models typically use autoregressive or diffusion methods. The autoregressive approach can work with pixel-based representations but often struggles with long sequences and low-resolution images. It can also involve complex pre-training for vector quantization. Diffusion models generate content through an iterative denoising process, which complicates their integration into standard LLM frameworks for multimodal systems. We propose modeling canonical codecs like JPEG and AVC, H.264 using conventional language model architectures for visual generation. While other works have explored file byte processing, they focus on visual understanding rather than generation and utilize specialized modules for byte sequences, whereas we employ a general Llama 2 model. Additionally, We note that JPEG formats can be effectively used with language models for file anomaly handling and generation, particularly for low-resolution images. JPEG serves as a universal codec for efficient image understanding, and some models combine generation with JPEG compression using GANs. Furthermore, learning restoration models to correct JPEG artifacts could enhance the image quality of our JPEG-LM generations. Lastly, compressive codecs are gaining attention in language, with some using canonical compressors as feature extractors for text and training language models to generate compressed text.